drunk. So I mean, it shouldn't make sense right now because you should be using all the data points, but there's a quirk of algebra that tells us we have to do n-1. Bear with, it'll make sense. So numerically, what would that be in this case? That would be 10, correct? 10 over, there's 5 data points, so 5 minus 1 is 4, which ends up being 2.5. Now the question I have is, well, the problem I have is, yeah, it's 2.5. 2.5 what? Like, what is 2.5 like? Like, we know what the average is. He averages 81 points per test. But 2.5 what? Let's chase the units. Let's chase units, shall we? Original data is right here, and that's in points, correct? That's in points. We then take points and subtract points, which leaves us with what? Points. We're still with points, so he's 2 points below average, 1 point below average, at average, 1 point above, 2 points above. Then we square them. What are your new units? Square points. So now we've taken the sum of squared points, 10 square points, divided it by a unitless number, so it's 2.5 square points squared. What the hell is that? Well, that's not a whole lot of anything. That's kind of meaningless, actually. In context. It's not meaningless statistically. It makes a lot of sense statistically. But for us, conversationally, it makes no sense at all. What we have to do is get rid of the squared points. And that's why the sample variance we don't talk about a whole lot in statistics. We talk about the square root of that bad boy, which we'll do over here on the sideboard. And this is called the sample standard deviation. And this is the biggie. This is the one, Rachel, we're going to come back to in 46.5 hours with your beautiful -2 to 2 and talk about. This is the one right here. The sample standard deviation. He's the biggie. There's also a population standard deviation. We'll get to him in time. We'll deal with him momentarily. And when I say momentarily, I mean like 3 weeks. Large moment. All he is, by definition mathematically, all he is he is the square root of the sample variance.
Which is 2.5
squared? Square root of 2.5.
Okay.
Yeah, exactly. He's also called S. He's got a little name, which is just S. Which is a very convenient name. Very often in this class, we use Greek letters. But you'll find out in this class, as we work through this class, the Greek letters are usually reserved for the population values. Mu is the population average. You'll see a lowercase sigma being the population standard deviation. We'll play with that as they come at us. The logical letters like S I love, because it stands for the sample standard deviation. So essentially, if we're going to call it S, and it's a square root of the sample variance, for Ernie, I'll put Ernie over here, Ernie, his S value, his sample standard deviation, is going to be the square root of that 2.5, which is approximately 1.5. What do you guys get? What do you guys get? Give me a better rounding than it's too low. 1.5 is too. 1.6? Jen, thank you. We get an approximate value of 1.6. 1.6 what? Say that louder. It's points, Jen. Why is it now points? Where did points squared go? Armando, right?
Yeah.
Help me out, my friend.
We destroyed it with the point squared.
We undid with the square root, huh?
Yeah.
We had points squared. We took the square root of points squared, which means it was 2-dimensional points. By rooting it, it becomes 1-dimensional points. So we're back to just points. So yay. Yeah, that makes sense. Now the unit on the standard deviation matches the unit on the average that it's being compared to. And here's the big takeaway. Here's the way I want you to think about sample standard deviation. Think of it. You have to use the word twice. You have to use the word average twice in the definition of what this actually is. Here's how I want you to process what the sample standard deviation is right now. Okay? Here's how we're going to process it. Think of it as the average distance a data point is from the average. Okay, that sounds a little weird because you have the word average in there twice, but good, it makes sense too, maybe good, good, good. It's the average distance a data point is from average. That's a really, really user-friendly way of processing what that number implies. It's a little bit false because Jen's definition is actually the perfect computation for that definition. Because when you took the absolute values and said -2 is just 2 away, +2 is just 2 away, and we averaged those and got 1.2, 1.2 if we made 6 divided by 5, that's technically the average distance. If we use the definition, our definition of average, which is sum of data divided by number of data. Well, if data is being defined as the absolute value from average, the sum of our data is 6, the number of data is 5, 6 divided by 5 is 1.2, done. And that's cool. But this is how I want you to think of this computation, which is essentially getting the same job done. So, yes, Ernie has a sample standard deviation of 1.6. Use that word in a sentence to describe what the 1.6 means. Start with 2 words, on average. On average, comma. I love that. On average, the standard deviation, well actually, we can take the on average out for that if you don't mind, Jordan. The standard deviation is 1.6. So let's use on average, comma, I'll get you started. This is a bit of a loaded question. On average, Ernie's test scores are 1.6 points away from average, Mimi. Thank you. On average, Ernie's test scores are 1.6 points away from average. And all of a sudden, we have a quantifiable measure of how to talk about Ernie's spread, don't we? On average, he's 1.6 points away. Now it's an average, so we lose the ones that are directly there, and we also lose the ones that are far away, which is what you're talking about, Rachel, over there. We'll get back to that, I promise you. 46.3 hours now. But the point is it jokes? But the point is that you now have a quantifiable way of calculating this average spread of data. Yay us! Yeah, I'm excited. It's okay if you're not. It's a foot of snow on the ground. You gotta drive home. I apologize. Not quite as excited as I am. Maybe we should let YouTube see what it looks like in Bend in April. Yes. Anybody thinking of moving to Bend? Remember, 300 sunny days a year, 38 inches snow on average per season. There you go. Mountains getting hammered, I'm sure. Cascade crud. There's a person wiping her car off over there. Yeah. Thinking about moving to Bend. Tax day, April 15th, baby. April 15th. So, I promised you that you would never ever calculate that by hand again, and I was not lying to you because that's annoying to calculate by hand over and over again. So, but Robin and everybody else, you kind of have to slug through a small data set. You have to, because you have to understand what the hell's going on. Why the squaring, for example? If I was to just put this formula in front of you and go, oh yes, this is how you calculate variance. And then you square the recipe and you don't. Well, it doesn't make any sense. Like, yeah, that's me telling you something, but it doesn't explain why it makes sense. Now you can see very quickly how this will get very annoying. If you have hundreds of data points, for example, it's annoying to even do it with a TI, let alone by hand. That's why in your on your take-home exams, I had you learn this kind of stuff in Excel. But for smaller data sets, the TI is a great tool. So bust your TIs out, and let's calculate Bert's values by TI, not by hand. We can actually recalculate Ernie's too with the TI if you want. So, let's fire these bad boys up. I'm going to use, I don't have a projector in here, so I got one fired up on the, whoops, not that one. Fired up on the screen here. And I think this will be, let's see how visible that is to the camera. I think it'll be good. Because I want to see not only the button pushes, but also the screen. Let's play with this. Bring it down a smidge. That is not terrible. Okay. Hopefully it's better than not terrible. Okay. The first thing, the button you're going to need to, well, turn it on first. Yes, that's a good start. Yay, on. the button you're going to be using, why is it blinking so quickly?
It's ready.
I'm palpating. So the button you're going to be using quite a bit in here is the stat button. Almost exclusively is your stat button. So fire up your stat button. In your stat button, or under your stat menu, you've got three options: edit, calc, and tests. I can tell you right now, we're doing nothing in tests. Nothing in there at all. That's 244. Everything in 244 is buried under that menu. Yay. That's fantastic. In edit, this is where we're going to start every time. So in edit, go ahead and select 1 for edit. What I want you guys to do is get used to putting data in right now. So let's put Ernie's data in L1. And let's put Bert's data in L2. And when I say put Ernie's data in, you just simply type in the values. So Ernie had exam scores of 79, 83. So I'm typing the data and then pressing enter after each one. 82, 81, and then I believe he had an 80 as well. It does not matter if you put them in order, because the average and the standard deviation are based off of addition, and addition is commutative. And if you want them in order, you can put them in order. We'll play with that later when it's important. It'll become important when it makes sense to become important. To get over to L2, just use your arrow over key. Arrow over. And then type in Bert's exam scores. He had 100, I know. Not 111. He had a 61, is that right? 82.
68 and 94.
Thank you, 68 and 94. Thank you, my friends. Why did I type 111 again? I was pretty sure I typed 100. Hang on. 100. There we go. Now I did. Cool. Then get 111. Now, let's recalculate Ernie's stuff first. Because the TI gives you a lot of cool stuff. A lot of it you don't need necessarily, at least right now at this moment, but it does give you cool stuff. So you got your data in, Ernie, Bert. Press the stat button again. These are all very cool. We'll use these in turn as we need them. But the big one right now, I want you to go to is calc for calculate. Scooch over one menu. And my favorite part, I think, about having this stuff recorded on video is the fact that in case you get stuck with computations in the TI, you can refer back to the video and go through the steps again. There are plenty of YouTube video tutorials out here, but this way at least you know where at least one is for sure. Okay, there's a lot of stuff in this menu. Lots. It goes way down, way down, way down, way down. The only one we're ever going to use in 243 is the very first one. One var stats. Now what that means is, one means single, var means variable. Exactly, Jordan, you got it. It means variable, and stats means statistics. Because all we're going to be doing in 243 is on a single variable. What is the variable we were measuring in the case of Bert and Ernie? What is the variable we were measuring? The points on their exams. That was the variable, right? It's called a variable because it was changing. Depending on which test we looked at, it had an 81, 100, a 61, a 68, a 94, an 83. It varies. It varies. And that goes on tight. It would be different if we were comparing Ernie's first test to Bert's first test. That would be two variables. You could argue that it's two variables, actually. So we're only going to be doing one variable stats in 243. So you're going to grab one var stats just by pressing 1 or pressing enter, and then go ahead and press enter again. When you press enter a second time, it gives you lots of good stuff. It gives you lots of good stuff. Let's explore what it gives you.
I think my calculator's too old.
Too old? Let me see what you got.
I don't have a stat button.
Oh, it's not too old. Yours is just in a different place. Give me 2 minutes after class.
Okay.
We'll kick out everybody a little more early. We'll get you squared away.
Awesome.
Yeah, the 89's in a little bit different place, Rach. It's all there. It's just a matter of finding it.
Okay, good.
Cool.
Because I was about to cry.
No, don't you cry. It's actually a newer calculator than these.
Okay.
And everything's menu driven versus these buttons driven. So we'll get to it.
How'd you get there again?
I just
The one of our stats.
So one more step, then just press enter.
Oh, enter.
And then boom. Now, please realize, and thank you for bringing that up, Addie, when you press one var stats enter, it automatically looks at L1. So it's ignoring Bert right now, only looking at Ernie. So you seeing some of the stuff we saw earlier? Recognize any of the numbers up there? What do you recognize first?
81.
Well, look at that. His average is 81 points. Well, beautiful, beautiful. Oh, guess I turned it off somehow. So 81 points. What do you think this is right here, friends?
Sigma cumulative.
It's big sigma of x, so it's the cumulative of
Points.
all his points. He earned 405 points over those 5 assessments. And you can see the 5 assessments, at least the number 5 right down there. So dividing that by that gives you that. I'm not sure why TI still has that summation x. Back in the day, a lot of teachers made their classes calculate standard deviations by hand, but not using the chart form. There's like some algebraic shortcuts you can do. So I think that's why these next 2 are still in there. What do you think this is right here? That's the sum of the squared data. So if you actually squared the test scores first and then added them together, that's what it comes up to. Notice it's different than our sum of squares, because our sum of squares is the sum of squared deviations from average, whereas that is actually the sum of the squared test scores. And again, I think the reason that's there, I think the reason that's there is, and if you want to geek out a little bit algebraically, if you want to geek just a tiny bit, this formula right here, you can expand. I'm going to put it on that. If you look, you take a trip back to Math 60. Don't write this down unless you really love algebra. Which is me. You're going to get some x squared minus 2x bars plus x bar squared. Binomial, FOIL, a plus b squared.
Squared.
Not squared. Thank you.
Yes.
Sorry, thank you. Very nice.
Squared.
Yeah, squared in the wrong place, outside. So now, if you wanted to do this computationally, you'd have to sum up the x bar squared. Well, that's that number, well, it's not off again, but it's that number on your TI. Minus 2 of these requires a summation of x, which was also one of the ones they gave you. And then you've got minus this summation of x bar squareds. So you see, you have all these pieces given to you right there. So I think the reason is the TI-83 operating system came out right around the time that people were still making their students calculate the variance or the sum of squares like this. So this was a way you could get students to calculate the variance without actually calculating the variance. You don't have to worry about a damn thing, because you could just skip over those two values, because they're not important for you guys. They're kind of a relic of earlier times. I love this one though, don't I? That, my friends, that line right there,
Sample stat.
that line right there is what you just calculated. That's what the whole point of this chart and that sideboard was. Wrapped up in that beautiful line right there, 1.6, approximately 1.5.
My question.
Yeah.
Should we actually do it until
Great question
the
Elena has.
tens
No,
or
this is a great
hundreds?
question. Fantastic question always comes up. How many decimal places do you round to? First of all, I'll always tell you. Secondly, there's significant figures. Ring a bell to anybody? Sig figs? Maybe sig figs-ish. Technically speaking, your final computation can't be any more precise than your least precise input. Your least precise input were our original test scores, which are all whole numbers. So technically speaking, we should round that off to 2, because that's the nearest whole number. But don't get your mind twisted around that. I'd like to leave it at sig figs, but I'm not exactly sure that's an industry standard. So I'll tell you, around the tenths, around the hundredths. Tenths is fine for purposes of argument here. Does that make sense as far as precision goes? Yeah. Well, I'll tell you what to round to. Don't sweat that. Turn itself off. The number directly below that that's a lowercase sigma. That's the population standard deviation. I'm going back to Rachel's point now about dividing by n-1 versus dividing by n. That's if you can, for the most part right now, ignore that number 2. This is the TI assuming that the 5 values you put into it were the exact 5 values in the entire population. Now, we've already talked about the problem with assuming that you have a population. You often don't. Most of the time, you don't. So for right now, ignore that value. Ignore that value. We'll come back to it when it's important to know about it. When we actually talk about probability distributions and the population of the universe that they kind of live by. There's your sample size. Scroll on down, and you get some more stuff. You get some more stuff. You get the min value, the smallest value you did, which is 79. Don't worry about Q1 yet. We'll deal with him on Monday as well. Look at that. Gone are the days of listing things out in a row and finding the middle. It'll give it to you. Yay. Yay. Q3, ignore him too for now. We'll get him on Monday. And there's your max value. Yay. All this is wonderful. All this is wonderful. Now, This is Ernie, but we knew all this already for Ernie because we calculated it all, right? We want Bert. So, what you're going to do, go ahead and hit clear again. Go back into stat to calculate. Okay, so we're going to the exact same trip we just took with Ernie. Press enter again. You're in one of our stats. Now, don't just press enter again, because you're going to once again get Ernie's data again. What you have to do now is tell the TI, okay, I got to look at where Bert's data is, which is L2. And the way you get L2, can you see right above your 1, 2, 3, 4, 5, and 6 buttons? There's a L1, L2, L3, L4, L5, and it's a little blurry on mine, but yours it won't be. So you press the second button, and then whatever list you need. So I'm going to press second 2. And now it says 1 var stats L2, and it will now do the exact same computation on the data in L2 versus L1. Press enter. Is it broken? I see the exact same average and the exact same sum of x. Is it broken? No, this was the problem, right? Bert and Ernie had the same average. We're getting a reassurance that yes, you did calculate the average correctly. The average, Bert's average is 81, which means he had the sum to the same amount of points. You start seeing a difference here, though. You start seeing a difference in the sum of the squares. Again, you're not actually looking at this. You're looking at this, aren't you? You're looking at Bert's sample standard deviation, which means Ernie's sample standard deviation clocked in at 1.6 points on average per exam. Bert's is clocking in at about 10 times greater. It's about 10 times greater on average per exam. Now, does this make sense to us? Does this make sense to us in our guts? Hopefully, because here's what the takeaway is. Yes, average distance a data point is from average. As Mimi so correctly said earlier, when Ernie's sample standard deviation, let's slap this over here again. When Ernie's sample standard deviation was 1.6, she said that means on average, Ernie's test scores are about 1.6 points away from 81. Perfect. Bert has a sample standard deviation of about, I should do squiggles. Is it cool if I do squiggles?
Yeah.
16.6 points? 16.6 points?
Yeah.
So, tell me that in a sentence. What does that mean? Yes, his sample standard deviation is 16.6 points. So use that in a sentence to tell me what that means. Explaining it to your neighbor. You're out there trimming your hedge on a beautiful spring day. It's snowing. You trim your hedge anyway in Bend. And your neighbor wants to know what a standard deviation is. So you say, well, simply it means for Bert that...
Standard deviation of Bert's points is 16.6.
Yes. So on average,
Average of an average.
Bert is 16.6 points away from 81. And your neighbor says, that's awesome. Here's your thatching rake I borrowed 3 years ago. Have a great day. And then you're done. So now you have a quantifiable way of identifying the spread. We're happy too, because Bert's is bigger than Ernie's, and it should be because his data is more spread out. But now we've got a quantifiable measure. So essentially what you're looking at visually, just to refer to this image one more time, this image up here. We now know that if we take Jen's awesome idea of simply looking at the distances from these data points in, we know on average the length of the line I just drew out from the blue line is 16.6 for Bert and about 1.6 for Ernie. That's it. We're happy because we've got large standard deviations mean that the data is what? Large standard deviations mean the data is what? Spread out. And small standard deviations mean the data is clustered. Good. Anybody concerned with the word small versus large with respect to this? Right? What is small? What is large? Clearly, Bert's is larger than Ernie's because it's 10 times bigger. But suppose Ernie's was 1.6 and Bert's was 0.25. What about that? How do we get, don't worry, that's what the whole course is about, is weighing that variation and trying to figure out how big is too big to be beyond acceptable. This is where we get back into Haley's point about -2 to 2 in that range. But we'll get into that on Wednesday, I promise you there. Okie dokie? All right, that's a good place to stop for today because the next thing's going to take more than the time we have left. Don't worry about homework.